Okay, we're done with thermodynamics. We're skipping chapter 16. So now we're in chapter 17, section 1, still in physical chemistry, obviously. Chapter 17, we're beginning kinetics. There are two types of kinetics. And this is a lot newer than thermodynamics by decades, easily. Now, the first kind was physical kinetics. I say was because that's what chapter 16, which we're skipping. Because that's mostly for engineers, and the target audience for this is chemists. So, transport processes. So you've got A, you're still going to A. A is actually a region or substance, but so example would be diffusion. Like, if you put two liquids together, how fast do they mix or whatever. Fluid dynamics, how fast do liquids move around, fluid mechanics, etc. So it's not really chemistry anyway. The second one is chemical kinetics, chemical reactions. Like if you got chemical A going to B, how fast is that going to happen? So there's going to be the rate that A becomes B, or also the mechanism, exactly how does A become B, what intermediate steps, etc. Okay, continue on physical chemistry, chapter 17, section 1. There are actually two types of reactions for the purpose of what we're doing. The first is a homogeneous reaction. Homogeneous reaction is one that occurs at only one phase. An example would be pretty much any gas phase reaction, because all the gases are completely miscible and it's all one gas phase. Or likewise, if you have a liquid solution and everything is completely dissolved in each other, so they have one liquid phase. Any reaction that happens like that is going to be a homogeneous reaction. So by the process of elimination, heterogeneous would be a reaction that occurs in more than one phase. A couple examples here. One, the catalytic converter in your vehicle, it's got solid phase metals like palladium or something like that. And then, of course, the exhaust coming out is gas phase. So the reaction is actually happening on the surface of the metal there. And likewise, another catalytic reaction, you've got C2H4, I guess that's ethene, and that's a gas, and then hydrogen gas. Then you've got a couple of metals as your catalyst, making another gas here, I would assume. Anyway, so now we're going to talk about a generic reaction. And we're going to be speaking for now only in homogeneous systems. So you've got A moles of A plus B moles of B, C moles of C, etc., for your reactants. One way for now, we'll talk about reversible reactions later. And then, so you have E moles of E plus F moles of F plus you can have unlimited. And of course, we're going to talk about a closed system for now because we don't want to throw in that extra mathematics. We just want to talk about the actual reaction. Now there's actually two ways to measure the rate of reaction. So one is the rate of conversion. This is capital J. Yes, it's the same as joules, but oh well. So for each reactant, you've got a minus sign in front because you're losing it. So you have minus the 1 over A, that's the stoichiometric coefficient, same as nu, times the differential of the number of moles of A divided by the differential of T. T is time, lowercase t is time. And that's going to be equal to every single one of these terms. So for each reactant, you have minus 1 over the stoichiometric coefficient of the reactant times the differential of the number of moles of the reactant divided by the differential of time. And then for each product, it'll be exactly the same, except it'll be positive because you're gaining product, obviously. So you have 1 over the stoichiometric coefficient of substance E times the differential of the number of moles of substance E divided by the differential of time, etc. for F, G, H, whatever you have. Continue on physical chemistry, chapter 17, section 1. So we just talked about the rate of one rate. Now we got a different rate, the rate of reaction R. And that's defined as the J we just defined divided by capital V. Capital V, remember, is volume, just like we did before. Hopefully you're familiar with this notation. An A in brackets means the molar concentration, like molarity. So the concentration A, and that's for substance A. We're talking about substance. So this rate here, using J and converting units here, substitution, we've got this lowercase r, rate of reaction, is equal to minus 1 over A times the differential of the concentration of A divided by the differential of time. And so that's going to be the same for any of the reactants with a minus sign in front. So you got minus 1 over B, the minus sign tells you it's a reactant, times the differential of the concentration of B divided by the differential of time. And then here we have a positive, so we know this must be a product. So we have 1 over E times the differential of the concentration of E divided by the differential of time. Because we're talking about the reaction going from reactants to products, we're going to be losing reactants, gaining products, so by definition R has to be positive. Now over here on the left side, any of these reactants, the R is what's telling you is the rate of the disappearance of that reactant, or the consumption, how fast that reactant is being consumed. And likewise on the right side of that balanced equation we have any of these other products, the right side is all the products, so R is telling you that the rate that this is being created or formed, the rate of formation. Now the units for R, for any type of reaction, it doesn't matter, is always going to be moles per liter per second. Of course, moles per liter is molarity, so you can write as molarity per second, or just molarity second to the minus 1 if you want to get it on one line. Since it's per volume, of course, R is an intensive quantity. Now what we're going to do now is talk about rate loss. Rate loss is basically how fast this happens is going to be dependent on the concentration of A to some power, we're going to call it alpha for now, times the concentration of B to some beta power, etc., to all the different products and reactants, and possibly other things to the whatever power. Notice this is proportional to. We've got to convert that to equal sign somehow. Now these exponents up here, the alpha and bravo, it's beta, alpha, beta, etc., lowercase lambda, these are numbers, real numbers. They're usually integers, but it's also sometimes common to see them as half integers, like 1/2, 3/2, 5/2, etc. Continuing on physical chemistry, chapter 17, section 1. So that rate law we had in the previous one, remember we had a proportional to and all these terms. To make an equal sign, what we did was we introduced a constant, lowercase k. So this here is a generic rate law. Now this k, this is a reaction-specific constant. If you have different reactants, products, or whatever you've got over here, you're going to have a different k. And it's the same symbol as the Boltzmann constant, lowercase k, but this is not the Boltzmann constant. Now, k in this case is called a rate constant because, well, this is a rate law, and it's the constant for the rate law. K is dependent on both temperature and pressure. Now, K is very strongly dependent on temperature. We'll see later on in the chapter why that is. But it's only weakly dependent on pressure. So for now, or pretty much forever, we're going to ignore the dependence on pressure. Now, rate law, remember, is determined experimentally. You cannot just guess it from the balanced equations. So if alpha is the order with respect to A, so we're going to start to talk about order of reaction now. So let's say this alpha is a 2, then we say this is a second order reaction with respect to A. If this beta here is a 5, then we say this is a fifth order reaction with respect to B. If this lambda is a 1, then we say this is a first order reaction with respect to L. Now if you add up all the exponents for whatever is in the rate law, alpha, beta, lambda, etc., that is defined as N. And N, this is lowercase n obviously, that's your overall order. And unfortunately, yes, it's the same lowercase n as the number of moles, but anyway. Okay, continuing on physical chemistry, chapter 17, section 1. So here's some examples of rate laws. So I made two columns here, one for the reaction and one for the observed rate law. Remember, I emphasized observed because you can't tell the rate law from the balanced reactions. You have to go out and actually gather data, do experiments. So an easy one here, we have hydrogen gas, diatomic, plus iodine gas, diatomic, going to hydrogen iodine gas. Oops, that's not balanced, is it? Whoops. Anyway, but you get the idea. So the rate is just going to be the constant times the concentration of hydrogen times the concentration of the iodine. This is easy to understand because, you know, these both reactants are here. And each one, there's a 1 there. You can always leave out the 1. So we say that this reaction is first order with respect to the hydrogen, first order with respect to the iodine. Therefore, you just add 1 plus 1 and get 2, and the reaction is second order overall. Now the second thing, remember, this K is specific to the reaction. There's going to be a K for all these, and it's a totally different K. So likewise, we have 2 N2O5 gas falling apart, or breaking up to 4 NO2 gas plus O2 gas. So the rate of reaction for that is going to be K times the concentration N2O5. Again, this is a first order reaction, and again, this is a simple one because the only thing in the rate law is the reactant. Now here's a more interesting one. We have CH3, CHO going to CH4 and CO. the rate this time is R is equal to K times the concentration of your reactant to the 3/2 power. Remember what I said before, that this exponent, it can be anything. It can be, it can be any real number. It's going to be positive, almost always positive, but it can be an integer, half integer, weird fractions, whatever. So, so this is the 3/2 order with respect to this substance, and again, the overall order of the reaction is 3/2. So here's another one with only one reactant, H2O2, hydrogen peroxide, aqueous. We have a catalyst this time, iodine ions, whatever. So become water and oxygen. So R is equal to K times the concentration of your reactant, but also times the concentration of the catalyst. So again, this is first order with respect to H2O2, hydrogen peroxide, and first order with respect to catalyst, so it's overall second order. But life isn't always so simple. Here's an interesting reaction, H2 gas plus Br gas. Notice it looks almost exactly like the first one. I and Br, they're even in the exact same column. So looks like it's a very similar reaction. And then you get 2HBr. This one's actually balanced. This is bugging me. All right. So, as you can see, the rate law comes out extremely complicated. We have K times the concentration of the hydrogen, which is one of the reactants, times the concentration of the Br. Should that be Br2? Whoops. Okay. So that's one of our reactants, to the 1/2 power. And then we have 1 plus J, which is another constant. So this one has two different constants, times the concentration of the product divided by the concentration of the reactant again. So for this one here, you don't have to worry about trying to say it's first order, second order. Don't worry about the order of the reaction, because it's kind of ambiguous the way there's fractions here and stuff. Also remember, not only are all these K's different from each other, specific to each reaction, etc., plus it's dependent on temperature and pressure, but you also had a constant in the equilibrium reactions, and don't confuse the constant for this rate reaction with the constant for the equilibrium reaction. It's a totally different thing going on. Okay, continuing on physical chemistry, chapter 17, section 1, we're talking about mechanism now. So, anytime you have a reaction, we know it goes from reactant to products, but in between there can also be 0 or more intermediates. Now, mechanism is the sequence of elementary steps that constitute the overall reaction. That's called a mechanism. Now, for an example, let's do this reaction here. 2N2O5 going one way to 4NO2 plus O2. This is the overall reaction that we're analyzing. Now, for a plausible mechanism, we're continuing three separate elementary reactions. So one of those elementary reactions, you start with the N2O5, and that's in equilibrium with NO2 and NO3. Now normally for balancing a reaction, you would just have 1, 1, 1 here. In fact, you can do that, you probably should do that, but I'm going to show you in a bit why we put 2, 2, 2 here anyway. Now it's important to pay attention to what you're doing. You probably used NO3 minus being a nitrate ion. This is not a nitrate ion, this is an NO3. This is a neutral species. It's exotic because it's actually a radical. It's got like an odd number of electrons or something. So then the next one is going to take some NO2 plus NO3 and then go to NO plus O2 plus NO2. And the third elementary reaction is NO plus NO3 plus 2NO2. Notice we didn't imply what order these reactions are going to happen. This one has to be first, of course, but out of these and so on, it's kind of ambiguous what's going to happen. If you add all these stuff up, literally, some of the stuff is going to cancel out. Like you have NO2 here and NO2 over here. You've got, let's see what else. We have NO and NO. NO. Let's see, we have NO3, NO3, two NO3s. So cancel those out. Alright, so what we're left with, is there anything I missed? Did I miss something here? So we have 2 NO2O5, same as the original reaction, and then 4 NO2, good, plus O2. Okay, so after everything cancels out, matches the overall reaction that we're trying to analyze. That's a good sign, just like Hess's law. So you'll notice then, we have in these elementary steps, there are a couple of species, NO and NO3, that are not reactants or products. So these are called intermediates. And when you do this, the intermediates should cancel out, which they did. Okay, continue on physical chemistry, chapter 17, section 1. So we showed on the previous slide how a reaction can have intermediates. These intermediates, they typically don't last long. They're just created and they disappear right away. A lot of them are, unstable radicals or whatever. But we can use spectroscopy and other techniques to identify these intermediates to try and verify if our mechanism is plausible or not. Now, the mechanism for reaction is not necessarily unique. There can be different routes for the same reaction to happen. Now, we can't really prove a mechanism is true either. If we got evidence to support it, like, identifying those intermediates, then we say that mechanism is plausible. Now, S is a stoichiometric number. Now, remember before how I showed you N2O5 and NO2, this reaction, this is the same as, we're in the same example still. I said you could have 1, 1, and 1 here. But that is true. But you realize to get all these to add up and balance out, this reaction has to happen twice. So S for this reaction is 1, S for this reaction is 1, and then S for this reaction is 2. Now, remember, nu is the stoichiometric coefficient though. Like here, nu is 2, 4, and 1. So for nu, it could be different for each species, but it's got to be overall for the same reaction. Like here, you'd have 1 for nu, 1 for nu, 2 for nu, but S is overall 1. So don't confuse the stoichiometric coefficient with the stoichiometric number of the reaction. Alright, continue on chapter 17. We are finishing up section 1. So here's another reaction. We've got ethylene, double bonded carbons here, plus another a diene, 1,3-butadiene. Those are going to react to make cyclohexene, C6H10. It's believed that this happens in one step. So, just because you have complicated molecules doesn't mean you're going to have a complicated rate law or anything like that. You've got to go to do an experiment and find out for sure. Now let's talk about what is a pseudo-order reaction. Here's an example of a reaction. We've got sucrose plus water in a acidic solution, and that'll give you glucose and fructose. So for the whole reaction here, we have R equals K double prime times the concentration of the sucrose times the concentration of water to the 6th power times the concentration of the acid. So that gives us 1 plus 6 plus 1 equals 8. This is an 8th order reaction. But if we're actually doing this in a solution, and we might have a buffer or something, so we can keep the concentration of the acid constant. Actually, acid should be constant anyway, because you'll notice it's not a product or a reactant, it's just a catalyst. So a catalyst, the concentration should be constant. So we can actually get rid of that for a typical solution and say, okay, then rate is equal to K prime times the concentration of the sucrose times the concentration of water to the 6th power. Likewise, if you're doing this in an aqueous solution, it's likely that you're going to have so much water, the water is in excess, that it's going to stay roughly constant. Therefore, that you can even leave that off and say, okay, the rate is just going to be equal to a different constant. That's why we have the double prime, single prime. So just a constant times the concentration of the sucrose, and which is always the 1st power, because this reaction is 1st order with respect to the sucrose. So now, by keeping the water and the acid constant, we've made it look a lot like a 1st order reaction. So we say this is a pseudo 1st order reaction. Continuing on physical chemistry, chapter 17. This here, what you see, is all we're going to do for section 2. Section 2 talks about measurement of reaction rates. The main thing is there are 2 types. One is chemical methods. First, you usually need to stop the reaction. One way to do that is simply dilute it, because remember, the reaction rates will have concentration. You decrease the concentration, you decrease the rate, you've effectively stopped it. And then once you stop the reaction, you can analyze it using gas pilorimetry or mass spectroscopy or whatever to see, hopefully you can recognize your intermediates and see what's going on. This is a less preferable way. The other way is what we call physical methods, using instruments and so on. This is more accurate and is quicker than chemical methods. Like I said, spectroscopy I mentioned before, and so on.